Hey, this is 1.3 on rate of change and slope. So what we're going to look at today is that you're going to be able to find rate of change and also find and determine the slope of a line. And so our standard here is FIF6. And so looking at being able to determine the average rate of change of a function over an interval and also their meaning in a given context. And so let's look at this first example. College admissions in 2017, 34,921 first-time college students applied to a state university. In 2012, 24,136 students applied. Find the rate of change in the number of first-time college students applying for admission from 2012 to 2017. Well, first we need to find how many students of a difference this was between those years. And so we're going to subtract the 34,921 from the 24,136. And when we do that, we've got 34,921 minus 24,136. That's 10,785. So that's how many different students, more students, were applying per year, or over those 5 years. But that's what we need to find, is the average rate of change. And so how quickly did this change over those years? So the 2017 minus the 2012, that gives us 5 years. And so when we divide that number by 5, we get 2,157. Now, as you saw in the standard, we need to apply this back to context. And so what this 2157 means is that there were 2,157 students. So 2157 more students applying each year. And just to make a complete sentence, there were 2157 more students applying each year on average. Because obviously we don't have the numbers for 2013 or 2014 to look at. In B, we're going to find the rate of change from a table here. And so we see we've got some times, we've got some distances, and we've even made this multiple choice. And so if this is a linear function, we could pick any two. And if we look at the pattern here, we could see that 2 times 3 would give us 6, right? 3 times 3 would give us 9. 4 times 3 would give us 12. 6 times 3 would give us 18. And so that means that this is increasing at a rate of 3 feet per minute. Because at 1 minute, we'd be at 3 feet. At 5 minutes, we'd be at 15 feet because the pattern is consistent. If the pattern's consistent, then we're good to go on this. If the pattern's inconsistent, then we have to go with the average and we have to be given certain points to use, like we did in the first example. As we look at example 2 on average rate of change, we look at this graph here below. It says, this graph below shows data on the fastest growing shoe stores chain in the United States between 2011 and 2016. So we got to interpret some data from this graph. And so we're looking between these years. So it's the only two I care about. I don't care about any of these other points. I don't care about this one or this one or this one or this one because these are years since 2010. So this is 2011 and that's 2016. So if we look at our data points here, this point is at 6, comma, and if we look across, it's at 34. And if I look at this one, this is at 1, comma, 7. Now, please note, look at the graph here. These are in thousands of stores, and these are years since 2010. And so that's why we get our period of 2011 to 2016. And so we set this up like the first problem. So 34 minus the 7, because that's the difference in stores. That gives us 27. 6 minus 1 gives us the 5. And so 27 divided by 5 is 5.4. Remember, these are in thousands, though. So that means that on average, there were 5,400 stores opening each year between 2011 and 2016. So again, we can see that this is not a linear function. You see there is some curve to it between, for example, like 2014 and 2015, the curve starts to get sharper, and 2015 and 2016 also the curve gets even sharper there. So it's not a linear function. If we had found between 2011 and 2015, this number would be smaller because it's not going to be 5.4 because it's only from 7 to 25. And so that over 4 years is a little bit less than 5.4. Okay? So as we look at the next example here, example B. In the graph at right, we're going to find the average rate of change of the percent of households with computers in the United States from 2000 to 2004. And we've got some options here. We've got a couple that are values, some million number of houses per year, and we've got some that are percentages. So ask ourselves, based on our graph here, we've got the percent of households over years. So we're not looking at the number of households, we're looking at the percent of households. So immediately options A and B are eliminated. And so as we look, we're looking from 2000 to 2004, and these are years since 2000, so at 0 we're at 2004 would be 2004. So again, I do not care about these data points in the middle. All I care about is this one and this one. This one's at 61%. This one's at 70, looks like 75%, 74% maybe, because these are broken up to 4, 6, they're broken up in that. So yeah, that's 74%, because they're broken up into quarters. So as we look at this data, we're going to go 74 minus the 61 over 4 minus 0. So we're going to get 13 divided by 4. And 13 divided by 4 is 3.25. Now, they try to trick you with this one. They put 3.25 million per year. But again, we're not dealing with millions of households here. We're dealing with percent of households. And so our answer has to be C. So let's talk about slope of a line here. What is the actual definition? And again, this is stuff that you should know from 8th grade, Algebra 1, so on. But just again, reaffirming it here. The slope of a line is the ratio, and remember ratio means division, of the change in y coordinates to the change in x coordinates. And so we write it out. This is the formula you're used to. M is equal to y2 minus y1 over x2 minus x1. And that's equal to this piece that we've added in here. This piece here, this little delta, this is the Greek letter delta. So that's the Greek letter delta. And what that Greek letter delta means is the change in. That's what it means in math. And so as we read this is the change in y over the change in x. And so this is what we're getting from these formulas. And so as we look at example 3a, find the slope of the line that passes through the points. So m is equal to, we label this out x1, y1, x2, y2. And so we will do y2, so that's negative 2, minus, it's always a minus here in the middle at first, 4, and then 1 minus negative 1. Make sure you get your signs right. The second step is where you can fix those signs if you need to. So negative 2 minus 4 over 1 plus 1 as we do the double negative. And so that gives us negative 6 over 2. So that's equal to negative 3. So the slope of the line that passes through these 2 points has a slope of negative 3. And remember, negative sloping lines, as we talk about them as they go from left to right, so that would be sloping downward like so as we look across the coordinate plane. Example B, we've got 9, negative 3, and 2, 7. So try this one on your own. Pause this real quick. Pause it right now. Do the work, and then come back and look at the answer. Did you pause it? I hope you did, because here's the answer. So m is equal to 7 minus negative 3 over 2 minus 9. And so this is 10 over negative 7. Does that reduce? No, 10 and 7 don't have anything in common. We could convert this to a decimal, but we're divided by 7, so that's going to be an ugly repeating decimal. So leave it as is. The only thing we're going to do is we're going to move that negative either up to the top with the 10, up to the numerator, or we're going to move it out front, negative 10, 7. So again, either one of these, move that negative so it's not in the denominator of your final answer, please. Okay. Last examples here, looking at example 4, slope from a graph. And so we just need to take the ordered pairs from the graph and get it, or remember you could do rise over run here, look at your rate of change. So in this case, we're going up 2, right 4. So up 2, right 4. And so remember, it's the change in y over the change in x. Our change in y was 2. Our change in y was 4. Remember, if we're going up, it's positive. If we're going right, it's positive. If we'd gone the opposite direction, it'd be negative, negative. Reduce as needed. Simplify signs as needed. So 2 over 4 becomes a half. The slope of this first line is 1/2. And finally, example 2 here. We look at this one. And so we're looking at these ordered pairs here. Again, we could plot out the points. We could get our x1s, y1s, x2, y2. But when I'm given a graph, I just like to go and just draw on it, especially when I've got something I can draw on. So I'm going down 2 here, negative 2. And you always see me work the vertical first because remember, it's the change in y. So that's the vertical component over the change in x. So my vertical is to go down 2. And I'm always going to work left to right as well because that's the natural way we talk about graphs. So down 2, and then I'm going right, and as we count this out, this was at negative 8. Negative 7 if I can count right. 2, negative 5, negative 6, negative 7, negative 8, 9. 10 is going to be off the screen there, it's the edge. So this is negative 7, and then so 7 and 2 is 9, so negative 2/9. And so we look at the options, that is A. If you had reversed this over and done 9 over 2, you would get this negative 4/2. So be careful that your x and y are in the correct places. That's all the notes. If you got any questions, you know what you got to do, ask. I'm always here for you. By the way, we left the word of the day to the end, and the word of the day is MLK. Again, that's for Martin Luther King. So MLK is the word of the day. Y'all have a good one.